Hey, welcome to Unit 8, Section 3. This is one of the top 3 lessons in all of Unit 8. All right, we're going to talk about rotations and symmetry. We have a lot to throw into this lesson, but I don't think it's too difficult. We're going to talk about what a rotation is. You know what a rotation is. Look, when this thing gets flipped up 90 degrees, that's called a rotation. And if you keep rotating it, it'll go to 180 degrees, 270 degrees, which is the same as rotating it the other direction, 90. We're going to talk about that more later. And then if you rotate it all the way around, that is 360 degrees. Okay, they're exactly what you'd expect. A transformation that turns it around a point. When we're graphing, that point's always going to be the origin, 0, 0. So what you need to conceptualize is a point on the graph paper. You take a nail, you put it right through the origin, and then you spin the paper. And that's the type of rotations that we are going to do. We are always going to rotate counterclockwise. It's the opposite way the clock goes. Someone's going to have to tell Sully how this works, because a clock, sometimes that confuses. Look, clocks go this way, all right? Well, we want to go counterclockwise, so we're always going to go this way. We'll rotate this way. And if we have 3 examples here, and I use 3 different points to show where we rotate. So the first one, we have triangle ABC. All right, so there's point B. That's what we're rotating around here. It's like taking a nail, driving it through point B, and then spinning the paper. All right, if you wonder why this is actually 90 degrees here, how you figure that out? Well, let's take line AB, and then the new triangle will take A prime, B prime would be in the same place. And if you take AB and A prime, B prime, if you notice, that's a right angle. All right, same thing for the second example. We're rotating around point A. But you can pick any line segment from the original triangle, maybe AC, all right, and then A prime, C prime, that's a right angle. So that's rotated around point A, and here's one that's rotated around point C, and if you notice the triangle they're touching, they're adjacent, that will happen. You might even get the triangle to rotate onto itself depending on the number of degrees that it's rotated and which point. Okay, that's going to happen. All right, so the rules for rotating counterclockwise about the origin. First of all, I'm always confused because they say about the origin. It's same as around the origin. If you drive the nail through the origin and spin your paper, this is what's going to happen. But we're always going to talk in terms of counterclockwise. Counterclockwise is the way that we are going. So this is going to work very similar to reflections. I'm going to give you a rule, and you just have to apply the rule to the coordinates and get the new coordinates of the image of the pre-image. So if we look, the first rule I'm going to give you is a rotation of 90 degrees about the origin. Okay, so that means that you're going to rotate counterclockwise 90 degrees. Here's an abbreviation, capital R with a little subscript, 90 degrees. And what's the rule? The rule is negative YX. Okay, so I'm going to put that into words, and then we're going to figure out the other rules. So what are the words here? Well, you got to go from XY, you got to switch the order, and then make the first one the opposite. All right, so XY is the point we start with. Switch the order, and then make the first one the opposite, and that'll give us negative YX. Okay, so I'm going to take you here for a second. That's the rule for 90 degrees. Did you forget it already? All right, let's write it down. For 90 degrees, we take XY, we switch the coordinates. Alright, so that becomes YX, and then we make the first one the opposite. So there's the rule for 90. Well, the good part about rotating is if you rotate 90 degrees and then you rotate another 90 degrees, guess what that equals? That's a rotation of 180 degrees. So we can figure out a rotation of 180 degrees just from using our rule for a rotation of 90 degrees. All right, and remember, these are all going counterclockwise. So the rule for 180, well, that's just taking your image of 90 and rotating it 90 degrees again. All right, so that's why I use the words here, so we don't get too confused. You just switch the coordinates and you make the first coordinate the opposite. So if I do that with the image of 90, if I rotate it 90 and then rotate this 90, I should get 180. So what will that look like? Switch the coordinates, make the first one the opposite. All right, so switched, made the first one the opposite down here. So that's our rule for 180 degrees. How about for 270? Can you figure out 270? All right, so switch the coordinates of 180. Okay, we're going to rotate 180 90 more degrees. All right, so switch the coordinates, make the first one the opposite. So it's going to be, here's switching. All right, but then you got to make the first one the opposite. So the opposite of negative y would then become positive y. There's our rule for switching if you want to rotate 270 degrees. How about 360? That's 60 degrees or 90 degrees more. All right, so xy becomes, switch the coordinates, so that becomes negative xy, but then make the first coordinate the opposite. So negative becomes positive. But if you notice, look, we have xy being mapped to xy. It's basically being mapped to itself. This is called an identity type of a function or identity mapping, but that's 360 degrees. Remember, if you rotate 360 degrees, it's like doing this. All right, here we go. I'm going to rotate 360 degrees. There's 90. Here's 180. Flips it upside down. 270. 360 degrees. And guess what? You end up where you started. Okay, it's the same exact image, which is why xy goes to xy. So we have all of our rules now. All right, if you want to write down in words, switch the coordinates, make the second one the opposite, you can do that. Oh, it's not the second one. Who did that? That's wrong. Make the first one the opposite. Someone typoed that. Please keep in mind, a rotation of 270 degrees. All right, so if I take something and rotate it 90, 180, oops, terrible example, 180, 270, that's the same as going the other direction, only 90, right? There's 360 degrees all the way around if you rotate. If I go 270 in one direction, that's 3/4 of the way around. That's the same as 1/4 of the way around going the other way. All right, let's do that again. Here's 270, 90, 180, 270. Words are going top to bottom. All right, let's go the other way. 90. Words going top to bottom. So rotation of 270 degrees counterclockwise is equivalent to a rotation of 90 degrees clockwise. All right, you have to put that in your brain because they're going to give you questions. They're going to say 90 degrees clockwise. Bells and whistles have to go off. 90 degrees clockwise. These rules are only for counterclockwise. All right, 90 degrees clockwise is the same as 270, so just use the rule for 270 counterclockwise. That makes life easy. And remember that a rotation of 360 degrees, it's just mapping onto itself. You could only hope that that ends up on a mastery check. Okay, so the first example, find the coordinates of triangle ABC. All right, so we have A is at 2, 1, B 3, -1, and C is at -4, 0. We're going to do a rotation of 90 degrees counterclockwise. So the rule that we have is xy goes to -yx. That's the rule we put on the table there. So we need to switch the coordinates, make the first one the opposite. So A, which is 2, 1, would go to A prime, which is 1, 2. Make the first one the opposite. Voila, we're done. -1, 2. Everybody follow me there? Let's try B prime. I like to do both. I like to do like switch the coordinates and then make the first one the opposite. All right, so it's the opposite of -1 becomes +1. So there's that one. Okay, how about C prime? Okay, switch the coordinates. All right, it becomes -0. We can't have a -0, so just call it 0. We're all done. Voila, that's 90 degrees counterclockwise. Ta-da! How easy is that when you have the rule? That's awesome. Let's try this one. The rule xy goes to -x, -y. That's the rule for 180. All right, so where would D prime go? Well, D is at -2, 5. So the rule is for 180, -x, -y. So just take the two coordinates and you make them the opposite. So D prime goes to 2, -5. E prime would go to 0, -4. And F prime would go to 4, 3. Because I just made them the opposite. That's what the rule is. All right, it's that simple. How about example 3? All right, find the coordinates of GHF after a rotation of 90 degrees clockwise. You knew I had to throw one of these in. That's going the other direction. That's going the wrong way. So a rotation of 90 degrees clockwise, we are going to use, instead of that, we're going to use 270 degrees counterclockwise. It's the same image. So when we do that, we're going to use the rule xy goes to y -x. Okay, so what are we going to get here? G prime. That's going to give us, we got to switch it, make the second one the opposite for 270. That's what the rule is. So switch the order, make the second one opposite. So switching the order gives me this, and then make the second one the opposite. All right, so we get G primes at -7, -4. How about H prime? We're going to get 4, and then -2, then you make it the opposite, it becomes 4, 2. Okay, how about F prime? So you switch it, you get 0, -1, but you got to change the second one, so it becomes +1. Voila, done! Okay, I hope you can follow what I did there. I kind of talked through, but it's you can pretty much do it in your head. I mean, it's not that difficult. Here's example 4. We need to see what this looks like on a graph. Okay, so I will graph the first one, you guys graph the second one. Fair game? Deal. All right, so graph trapezoid trap. We have the coordinates here. We want to rotate it 270 degrees and see what that looks like. Okay, so here's the graph of trap. You might have to pause the video and then make sure you have it down there nice and straight. And the rule is for 270, we just dealt with that, it's you get y negative x. All right, so that means that t is going to go to 4, -0, which is just 0. That'll be t prime. R prime will be 1, +2, right? Because you got to change the sign there. A prime becomes 1, +5, and P prime becomes 4, 5. All right, so I'm going to graph these. T prime is at 4, 0. We're going to call that T prime. R prime 1, 2. All right, over 1, up 2. If you always forget, you got to go in the elevator before you go up and down. Remember? All right, 1, 5 is A prime. And P prime is at 4, 5. All right, so P prime. So now I'm going to draw the lines. And again, I know I'm going quick, but you can pause the video. So pause it if you need to catch up. All right, so this is what we get here. So what does that look like? Well, tell you what I'm going to do. I'm going to take a snapshot of the trapezoid here. Let's do that. Can I take a snapshot? How am I going to do that? Pause the... All right, so here's my snapshot. And what I'm going to do is I'm going to kind of shrink this down so it's mini size. All right, so what I did is I rotated this 270. Now, ignore the red over here. Ignore the red, my image. But let's look at the pre-image. What I'm going to do is I'm going to rotate it 270. Watch. Loving technology. So here is, watch pre-image, just purple. Watch purple. Here's 90 degrees. It would look like that. It'd be down in the, 1, 2, third quadrant. Here's 180 degrees. Okay, it'd be in the fourth quadrant. Here's 270 degrees. And if you notice, look, we now have the image exactly where this image is right there. All right, so this is why it's 270 degrees. If I went another 90, we'd be back where we started. Ooh, kind of wibble wobble there. So that is a rotation of 270 degrees. That's why it looks like it does. Sometimes it's hard to see that happening. Why don't you complete C and D, graph kite and the image of kite after a rotation of 90 degrees. Go. Okay, let's see what we have here. I put the rule down. Look at all this work. Oh, a little bit off screen. There we go. So xy goes to -yx. That's the rule for a 90-degree rotation. Okay, and always assume we're going counterclockwise. And if you notice, what do we got here? The original one's all in the third quadrant. Your image becomes in the fourth. It goes to the fourth quadrant here. It's mapped there. And so T goes to T prime, I goes to I prime. And if you notice, if you take like a nail and put it through the origin and you turn your paper, this would flip up over there. That is a rotation of 90 degrees. So how is that? That is pretty cool, right? So now we need to talk a little bit. Your last application problem involves symmetry and line symmetry. So we're going to talk a little bit about rotational symmetry and the order of a figure if it has rotational symmetry. An object has rotational symmetry if there's a center point from which you can rotate it in a certain number of degrees and the object looks the same. So here's some examples. Here's some road signs that we find all over the place. This one's priority road, and so I have it right here. This is called order 4 because we have 4 different points right here from which you can rotate this and it'll line up exactly the same. Let's look. Ready? I'm going to rotate 90 degrees. Ta-da! Now look, your image looks exactly like the first one here, the pre-image. You can't tell the difference. And so this has rotational symmetry. I can also rotate it 180 and 270. That's why we say the order of this one is 4, because there's 4 different points to the figure. Now, if you wanted to figure out how many degrees do I have to rotate it, Well, then, because there's 4 different points to it, you take 360, you divide by 4, you get 90 degrees. But we're not going to ask you to do that, but that's a little extra knowledge there. Ta-da! Not to the application, at least. How about order 2? This is for a bus. This is a bus sign. So if I rotate this all the way around 180 degrees, okay, remember 180 is all the way around. It's halfway around. Flip it upside down. If you notice, the 2 figures look the same. So we say that this sign also has rotational symmetry. How about this sign here, roundabout? All right, so this one gets a little more tricky, but everything's going to match up perfectly. So I need to rotate it about 1/3 of the way around. What's 1/3 of, look at, 1/3 of 360 degrees is 120 degrees. All right, so we say that this has order 3 because there's 3 different points to it from which you can rotate it, and it'll line up on top of itself. This image has order 2 because you can flip it over once and then bring it back again. Order 1, okay, see this horse? This horse messes things up because you can't, if you start turning it, it doesn't look the same until it goes all the way around. So we say there's only 1 point to this from which you can rotate it. That is rotational symmetry. All right, so let's take that concept and apply it to our alphabet. Which of the following letters have rotational symmetry? All right, so I'm going to start with an example here. Let's start with Z. That is an awesome Z. It's the best I can. But if you take Z and you flip it upside down 180 degrees, it looks exactly the same. I can't tell that it's been flipped, especially if it's been typed. So everything is nice and perfect there. So we would say that Z has rotational symmetry. All right, let's pick another letter. How about M? M. Love M. Let's start it. It's an M here. Not an M, not an M. It's W, not an M. M, M, M. Not until you come up. So this one does not have rotational symmetry. So go through right now, pause the video, write down all the letters with rotational symmetry. Go! All right, did you pause the video? Gabe, Ramstein kid. Gabe, pause the video. All right, so we're back. Here are the letters I came up with. They all have 180 degrees rotational symmetry except for the letter O, which you can rotate infinitely many different ways. I mean, 1 degree, 2 degrees, it doesn't matter. O is very symmetrical in many different ways. All right, how about reflectional symmetry? This is what we learned about last time at the in your application problem for 8.2. Reflectional symmetry is if you can draw a line down the middle and reflect it onto itself. So let's take the letter A. Everybody loves the letter A. If I put a line down the letter A, right down the middle, if I could draw my A properly, it would reflect onto itself. So A would have reflectional symmetry. Let me tell you one that people always screw up. Z and S. All right, here's Z. I'm drawing it the best I can here. And then they always think, well, look, if I take a line and I put it like this, it will reflect onto itself. That's not true. If I reflected this image, what would it look like? Well, it would kind of look like this. This would have to go up like this, and this would come down like this, and that would be, so the Z would flip over there. I mean, let's look at that again. If I reflected this point right here, remember you got to go to the line, it's the same side over, it would be right there. You can see that the letter that doesn't have reflectional symmetry. So go through right now and find all of the letters that have reflectional symmetry. Go! All right, I came up with these. Do you have any questions? Put your hands up if you have a question. All right, let's look at some of these. Reflectional symmetry. You can fold that down there. Reflectional, reflectional. This one's got 2. You can go this way or that way. Same thing with I. All right, K, you can go across the middle. M, you can go down the middle. This one you can do any way you want to. Okay, down, 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 down and across. Depends. Type it like this. No. Type it like this. Down the middle. All right, so that's it. That's section 8.3. We have rotations and rotational symmetry. It's all tied up there for you. Hey, you're going to love the application problem this time. It's going to introduce you to a little known art known as korigami. Korigami? What is that? This is Mr. Kelly Baumholder. Remember, it's nice to be important. It's more important to be nice. So